Hello everybody, we are now still on chapter 6 and this clip is for section 6.4. Okay, for this section we are go back to our function z equals to f of xy. Of course, it can be depends on more than two variables, okay, but let us just consider these two variable function first. Then previously you can find the partial derivative with respect to x and a partial derivative with respect to y, and you may notice that both of them, they are function of x and y. Okay, they are functions of x and y. So the question come to ask here that can we further find a partial derivative of these two functions? Okay, and of course we can, and we just did it before. For example, if you remember, what we have in a single variable calculus is that if you have y equals to f of x, then you can find the first derivative, okay, f prime x as a function of x, and then you can find a further derivative, the second derivative, okay, which is sometimes we call the higher derivative, f double prime, and then f triple prime, and we also have some other notation, right? This one is dy by dx or d2y by dx square, and d3y by dx cube, something like that. Okay, we also have another notation for this one as well, f sub x and f sub y, okay, this kind of thing. Then what will be a notation if you find a further partial derivative from the first partial derivatives, like that? Okay, so today we are going to continue our chapter with the so-called higher order partial derivatives. Okay, so as I told you, we just go back to two variable function first, and of course the first first order partial derivatives that you can find, okay, you can find the partial derivative with respect to x and a partial derivative with respect to y, and no more, right? If you need to find the first order partial derivative. How about the second order derivative? Then this one, as I told you, it is a function of x and y. Of course, you can further continue find a partial derivative with respect to x, okay, or you can continue find a further derivative, partial derivative with respect to y, and see where I point it down. Okay, and can you see where I point down? This one, of course, it has no ambiguity because we are finding the second partial derivative with respect to x one more time. So actually the way we write it, okay, this one, it is d by dx apply in front of dz by dx. Okay, so the way we apply this notation, this operator, okay, we apply in front of the function. Okay, so it means that this one, previously you have this, right? Because you already find dz by dx. Okay, this is the first partial derivative that you find, and then you follow by finding a partial derivative with respect to y further. Okay, so the way you write down, okay, this notation, it means that you do this one inside first and then you do the one in front follow. Are we good? Okay, on the same token, if you finding the derivative with respect to y, okay, the first partial derivative with respect to y, and you find further with respect to y, then of course this one, okay, this is the first one that you find, put it inside, and then follow by this one, put it up front, so you have a d2z by dy square. Okay, has no ambiguity. However, if you look at this one, okay, it means that the one that you calculate first, it is dz by dy, and then you follow by the one up front, okay, which is d by dx. So it is d2z by dx dy. Okay, so it means that the order of finding the partial derivative came from here to there. Okay, so it's from the right to the left. Okay, the right, okay, to the left, just like this. However, the one that you may very confusing is that if you use the another notation of a partial derivative, for example, you know, if you want to find the partial derivative with respect to x, it is f subscript x. So it means that if you find further, now the subscript will apply to the back, right, backward like this. Okay, on the back of the function like this. Okay, so it is f sub x and then sub x again. This one is called the f sub xx, and then if you already have f sub x and then you further finding second derivative with respect to y, this one is f sub xy. Okay, so now the order of finding derivative come from left to right. Okay, so they are a little bit different. Okay, on the other hand, if you have f sub y, okay, at the beginning, and then you find further derivative with respect to x, so this one is f sub yx, and if you have this with respect to y one more time, you got f sub yy. Okay, so, I mean, of course, if you finding derivative, I mean, keep finding derivative with respect to like the first variable x, then it has no confusing, right? Or the y, it has no confusing. But if you are order, I mean, switching between the first, the second, the first, something like that, then you may need to be careful a little bit by using a different notation. Okay, so the first notation is look like a fractions. Okay, it will put the derivative up front, and the second notation, if you're using the subscript, it will put the further derivative on the back. Okay, so you have 4 second order partial derivatives from your two variable functions. Okay, from your two variable functions. So let us start by the example. So this example, your f of xy is x cubed y squared and x2 y4. Okay, you need to find all second order partial derivatives. So of course, before you do that, you need to find f sub x first. So let me just use this notation first. So your f sub x, it is a 3. I mean, I'm not so sure whether you guys are familiar with finding the derivative already or not, but let me just go back to, you know, here is a constant derivative, go directly to the x cubed, so you have 3x squared, and here is a constant, you put it down first, derivative go directly to x squared, which is 2x, and then you simplify it a bit to have 3x squared y squared and 2xy fourth. Okay, and then you do the f sub y as well. So here x cubed is a constant, a derivative go to y squared, so you have 2y. X squared is a constant, a derivative go to y fourth, so you have 4y cubed, or you got 2x cubed y and 4x squared y cubed as your f sub y. Okay, so if you continue further finding a derivative one more time with respect to x, okay, or your f sub xx, again the 3y squared is a constant, so a derivative go to x squared, so you got 2x. The 2y fourth is a constant, derivative go to x, which is 1, so you have 6xy squared and 2y fourth. And if you do the other way around, you find further with respect to y. Okay, you find further with respect to y. Now the 3x squared is a constant, and the derivative go directly to y squared, which is 2y, and the 2x is a constant, derivative go directly to y fourth, which is 4y cubed, or you got 6x squared y and 8xy cubed. Okay, so how about f sub y? If you continue further with respect to the same variable y, so you have f sub y, so it means that now the 2x cubed is a constant, and the derivative go directly to y raised to the power 1, which is 1. 4x squared is a constant, a derivative go directly to y cubed, which is 3y squared. Or you can rewrite it as 2x cubed and 12x squared y squared. If you do f sub y first and then continue with respect to x, now the 2y is a constant, a derivative go directly to x cubed, which is 3x squared. A 4y cubed is a constant, derivative go directly to x squared, which is 2x. So we got 6x squared y and 8xy cubed. Okay, so here are the 4 partial derivatives. What can you notice? These f sub xy and f sub yx, they are actually the same. Either you do the x first followed by the y, or you do the y first followed by the x. I mean, usually in this course, okay, not only in this course, but in the function of two variable, 99%, okay, like 99%, they'll be equal. Okay, they'll be equal. There will be only some cases that is not equal, but we are not including in this course. Okay, however, even though they are equal, if we ask you to write it down, you need to write down in the right order. Okay, you need to write down in the right order. You know what I say? All right. How about this one? Oh, this one is already in terms of this notation. So what does this mean? It means that you start from here first on the right and then go backward like this. So the first one that you need to find is the derivative of w with respect to variable z. Okay, so it is a 3, 2x plus 3y, and the 4z. Just use the chain rule, right? Raised to the power 2. Then don't forget a derivative of the inside with respect to z. So the first one is a constant, the second one is a constant, and then a derivative go to 4z, which is 4. Or you have 12, 2x 3y, 4z square. And then you continue by finding a derivative with respect to y. Okay, so this one you have d2w by dy dz. Okay, so the 12 has nothing to do, and this one is chain rule, right? So you have to kick it down, and this one, the 2x 3y 4z raised to the power 1, and the derivative of the inside with respect to y. So the first one is a constant, the second one is 3y is 3, and the last one is also a constant. So you have 12 and 6, 72, right? And 2x 3y 4z. And the last one that you need to apply is a partial derivative with respect to x further, or it is a d3w dx dy dz. Okay, so the 72 has nothing to do, and then the derivative applied to this parenthesis directly, right? So it is 2 and then 0 0 because they are all constant. So you have 144 as a result. Okay, we good. Of course, I mean, if you want, then you may find the 3 y by dy dx dz will happen, or the 3w by d2y d1x, something like that. Okay, not d2y, dy square, sorry, and d1x, something like that. Okay, so you can play with your friends, okay, to find all these partial derivative. Okay, how about this one? If you want to find w sub x sub z and then sub x again, so as we told you, the order of finding from the left to the right, okay, just go it outside. So w sub x, the first one, of course, I mean this whole thing, they are constant, right? With a 4 as well. A derivative just go directly to x squared, which is 2x. So you have 8x y cubed 3z squared raised to the power 4. Next, what you are going to find is a further derivative with respect to z. So w of xz, and the z is right there. So of course the 8x is a constant, and then you need to use the chain rule. So you have a 4, you got y cubed and 3z squared raised to the power 3, and then a derivative of the inside with respect to z, so you have a 0, and of course 6z. Okay, and you can say that, hey, this is 20, this is 24 and 8, which is 192, xz and y cubed plus 3z squared cubed. Okay, the next partial derivative that you need to further find is the one outside with respect to x. So it is x, w sub x, z, x again. So of course here is the only x that survive, and the rest, they are now constant. Okay, and the derivative go directly to this term, which is simply 1. So this is, you know, your final answer, of course. If you want, you may find w sub x sub z and then sub y. Okay, what will happen? Or if you want again, sub x sub z, let's see, sub x and then sub z again. This will be more challenging. Okay, this will be more challenging. You can do it by yourself. Okay, so I mean, this is what we just notice, is that if your z is a function of x1 etc to xn, okay, the partial derivative df by dxi is the rate of change of a function with respect to xi, you remember, but the other variable are held constant. Okay, so if they exist, okay, if I mean all the first partial derivative exist, okay, of the first order, okay, so we have another n second order partial derivative, okay, which is d2f by dxj dxi, okay, which is the, of course, I mean, finding this derivative first and then continue up front. Okay, so it means that together we are going to have n square second order partial derivative. Okay, so for example, if you start with a function of two variable set of xy, you got two first order partial derivative. Okay, you got 2 first order partial derivative, and then you got 2 square of the second, which is 4, right? Remember just what we just did, partial derivative. So of course, I mean, if you start from a 3 variable function, okay, you have a 3 first partial derivative to start with. So after you find that 3, each one of them can find another 3 second partial derivative. So it means that you got a 9 or a 3 square of the second order partial derivative. Okay, so this is what they want to explain. All right, so by having that, okay, you can arrange, okay, you can arrange all the second partial derivative in terms of array, okay, of a row and a column. Okay, so by look at each row, you can represent each row by x, y, z. Okay, for example, this one is a function of 3 variable, and this column by also x, y, z. And when you read it, okay, you I'm not so sure whether you guys remember the matrix or not. Usually for the matrix, if this is a 3 by 3 matrix, we have the first row, the second row, and the third row, the first column, the second column, and the third column. Each one of them, okay, each element of them will call it by a row followed by a column. So for example, this one, this A is in the first row in the first column, this A in the first row in the second column, this one in the first row in the third column, like that. Okay, for example, this one is on the second row in the third column, this one is on the third row of the second column, something like this. So this matrix will call each element like that as well. However, instead of using 1, 2, 3, we use x, y, z. So look at this one. This is on the x row, the x column. So it means that you got f sub xx. For this one is on the x row, the y column. So you have f sub xy. This one is on the x row, the z column. So you have f sub xz. How about this one? This one is on the y row or the z column. So you have f sub yz. And this one is on the z row or the x column. So you have f sub zx. These arrangement of the matrix is called the Hessian matrix. Okay, it's called the Hessian matrix. All right. So for example, if you want to find the Hessian matrix of this one, so what you are going to need to find, of course, it will be your let me just arrange it as a matrix, okay, but it will be a pretty big matrix. This is, as we told you, the x, the y, the z row, okay, and you have the x row right here. So this one, it means that you need to find f sub xx, okay, f sub xx, of course, I mean, sorry, you need to find f sub x first. Here you have 10x, there you have y cubed, there you got 0, okay. How about f sub y? F sub y, this one you have 0. You got 3xy square, you have minus 2y z square, and then you got 0 for the last one. How about f sub z? F sub z, the first one has no z, so it is 0. So let me just don't write it. This one has no z again, so it is 0. This one, the derivative, go directly to z square, so you have 2z, so it is negative y square z, and then the last one, z cube, is 3z square. Okay, so this is each first derivative. Now you are going to find the second derivative, but arrange it in terms of Hessian matrix. Okay, so the first one, you continue further with respect to x, so you got 10. Okay, how about this one, the x row, the y column? So you need to find f sub xy, right? F sub xy. So you keep looking at the f sub x, right? And then continue further with respect to y. So you have 3y squared, and then the last column, it is the x row z column, and you're looking at the f sub x again, but then you find further derivative with respect to z, but right there has no z, so you got 0. Okay, so here's the first 3 element on the first row. Now if you're looking at this one, f sub y, and then continue by x, so it means that right now you concentrate on this second row, okay, f sub y, and then continue with respect to x, so you have 3y squared. Okay, how about f sub y and then continue with respect to y, so you have 2 terms, right? So let me just put it here. So it is 6xy and 2z squared, and the last one, f sub y z. Okay, so the z term is there, so you have negative 4yz. Okay, so what is the last row? So here the row is the z row followed by the x. Okay, so it means that now you concentrate on the first partial derivative, so there's no x there, so it means that your f sub zx is 0. How about the z row, the y column? So you have a negative 4yz and 0, and the last one is the z row and the z column, so you have negative 2y squared and 6z. Okay, can you notice which one that will usually equal? You see, f sub xy and f sub yx, they'll be equal. F sub xz and f sub zx, they'll be equal. And of course f sub yz and x sub zy, they'll be equal. Okay, so it will look like this one is a mirror. You see, the main diagonal look like a mirror, and then all these 3 pairs, they are equal. Okay, mirroring like this. Okay, this is the one of the properties of the Hessian matrix. Okay, of what we have learned as well, that this one, they'll be equal. Okay, comparing to this main diagonal. All right, of course, I mean, you can find this Hessian matrix again, okay, by yourself. All right, so this one, you can have f sub x, which is 3yz, 2xy, and z cubed. F sub y, 3xz and x squared. F sub z, it is 3xy and 3xz squared. Okay, and then you follow what I just told you to find all this. Okay, to find all this. However, the one that we usually will be used later on is actually the Hessian matrix of the 2 variable function. So of course, for the 2 variable function, you can find f sub x and f sub y, right? So the Hessian matrix, okay, will depends on only these 2 row and the 2 column, which is f sub xx, f sub xy, f sub yx, and f sub yy. Okay, and not only the Hessian matrix that we are going to consider, we actually going to consider a determinant. So we hope that you still remember that a determinant of a 2 by 2 matrix, okay, it is the downward multiply minus the upward multiply like this. So this one, a determinant of a Hessian matrix will be f sub xx, f sub yy minus f sub xy and f sub yx. But as I told you that usually the f sub xy and f sub yx will be the same. So what we end up with will be f sub xy squared. So this one is something that we are going to use later on. Okay, we are going to use later on in this chapter, the Hessian matrix of a 2 by 2 matrix, and especially a determinant of this Hessian matrix. Okay, so we are going to stop this clip right here, and we continue with something else later on with you. We'll see you then. Bye bye.